Hey guys, sorry I can't be there. What we're going to do today is exponential functions, which is pretty much a straight up review um, from last year, most of this. So let's talk about exponential functions. And we have to go through this because, um, hello, um, we're going to go into logarithms and things like that. So we got to review exponentials. So first off, from last year, hopefully, and actually we might have talked about this beginning of this year, we got f of x equals a times b to the x. And hopefully last year you learned that this a value is the initial value. And this b value is really called like a growth value. And there's a couple different ones. So like if b was greater than 1, it's a growth. And if it's in between 0 and 1, it's a decay. B can't be 1 because then nothing's happening to the problem, because 1 to the x, even the x changes, 1's going to stay 1. It's not going to do anything. So it can't be 1. So that was pretty much what we did last year. And also last year and the beginning of this year, we did ease e to the x, right? E is the natural base. And, it's like 2-point change, so yeah, 2.718, blah, blah, blah. So we can do some kind of relationship between this and with a base of an e. So here's how we do that. So I'm going to set up as a function f of x equals a. Initial value is still initial value, and that doesn't matter. E this time. But now notice that, so this b value is going to get absorbed in this e. So we're going to have to modify it with a coefficient. And so we call a lot of times coefficients k. And it's going to be k to the x. All right. So there's some kind of relationship between these two functions. And we can, given, enough time, we can actually determine, we can switch one from the other. Most of the time we don't switch between them. But a lot of times in biology, especially bio or, economics and things like that, it's going to be given to us as an e function already. So we have to be able to work with the e's. So with this whole function here, so now if k is greater than 0, that's going to be, well, k greater than 0 means, right, that's positive numbers. That's going to be growth. And if k is less than 0, right, that's going to be negatives. And that's going to be decay. If k equals 0, same as before, that would knock out, right? It doesn't matter, like if x was 0. If k is 0, that makes the top go to 0. That's just the initial value. It's just a constant number, so that doesn't really, it's not that interesting. So let's take a look at a problem with this. So this is our at book, page 288. So that's page 288. And this is question number 57. So we're going to look at what they wrote, and then we're going to modify it to make it a little bit, a little more universal, more, more useful. So this number of bacteria in a petri dish. And those little plastic dishes used in science or bio, should say. So it's a petri dish. And what they do is they put this like blue chemical, which is a growing medium in the bottom. It's agar, I think they call it. And after T hours, they count the bacteria. So what happens is you go to a place and they would come into the classroom, swab a desk, rub that on top of the growing medium, put it in a warm place for a couple of hours, and then count all the little white specks of bacteria growing on the top. Or they do this with people, they think they're sick. They put the cotton swab in your throat, grab it, they send it off to a lab. And that's what they do. So what they did is they give this formula, B equals 100 e to the 0.693 t. And the question in the book asks is, what was the initial number and how much was there after 6 hours? And that's pretty much how the book says it. All right. So let's some numbers here. So that's just the e value here. So let's clear this out. So I want to know initial number of bacteria. Well, I don't even need a calculator for that. The initial number of bacteria is going to be, well, plug in 0 up here, right? Or actually, I don't even need that. Just look at the problem. The initial number is 100. It's the number in front. If this was a 0, the whole thing goes to 0. E to the 0 is 1. 100 times 1 is 100. How much was there in 6 hours? All right, so that's going to be B equals 100 E 0.693 times 6. Now when you're typing this in, just make sure this whole thing is in a parenthesis upstairs. Okay. So 100. And actually over the ln button they have E with a caret. So you get the whole thing there. 0.693 times 6. Close it. And I get 6394. I'm just going to round it to the nearest, nearest number of bacteria, however they would say it. So that would be 6394.4 and change. And so that's the two answers. All right. Now, how would we? So let's make this a little extra. Okay. So why don't we write this in function notation? So they did not ask us to do this, but you should know how to. So write in function notation. Let's take a second, see if you can figure out how to write this in function notation using the same letters they use. Okay, so they have B and they have T. So instead of saying f of x, I'm going to say B of t. So B of t equals 100 e to the 0.693 t. So now let's do some different questions. Let's say find B3. Why don't we graph this function? For the first 10 hours. Okay. And then let's find where does B of t equal 50,000 bacteria. Okay, so we're going to do 3 things. 1, 2, 3. Well, hopefully, we're talking about graphing and finding B of 3 and finding 50,000. Hopefully you kind of put it together. We're going to need to type this thing in a calculator. So once you punch it in the calculator, and instead of t, we're going to use x, just like we did before. And so I typed it in, and I'm going to go to table and find a 3, and I get nearest numbers. I get 800, 799.65, so 800. But now the interesting part is I need to go to 10. So take a look at the values. This thing is getting really big. So I need to worry about this. So it's up at 102,000. Okay. So I'm going to fix my window. So now I'm going to graph this, but I'm going to fix my window. So I said for the first 10 hours, I'm just going to go 0 to 10. And I guess you can leave it at negative 10. It's not going to really matter because I'm going to make this max out at like 120,000. and I'm going to graph it. Okay, and it looks really small at the front because, you know, if you're looking at the table, right, these numbers are like 100, 99, so it's like 200, 400, 800, and then it really starts to grow. So once again, my window, 0 to 10, and 0 to 120,000. So where does B of t equal 50,000? Okay, so I'm going to graph 50,000. Oops. And so it's up here, 8, 9-ish. And we calc intersect it. Second, calc, intersect. And it occurs at 8.967, blah, blah, blah. So why don't we just call that 9? So let's write down some of these things. So t is approximately, what, 8.967, blah, 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 blah. So let's call that 9. The graph, we saw the graph, you had to fix that. B of 3, what did we say that was? 799.65. 799.65. But you can't have piece of bacteria, so let's just call that 800. And the graph was the window we saw, so I can redo that graph again. So 0 to 10, and I put it at 120,000. And it looked pretty much like a flat line at first. Like you can't even see it. And then it really started scooching up. And then we graph 50,000 like this. And that's our intersection. Let's try it again. Exponential regression. All right, so this is they actually use this as it's an example in the book or something or somewhere. So we're going to modify it though. So it says U.S. population is given by the chart, and the chart in millions. Okay, so here's the chart. So it says 1900. So, and it counts by 10. So 1900, 1910, 1920, 1930. And do that till 2000. And then they go to 2003 because that's when your book was published in 2005. They had data up to 2003. Okay. So in 1900, it was 76.2 million. And then 92.2. 106.0. 123.2. 132.2. 151.3. 179.3. 203.3. 226.5. 248.7. 281.4. And 290.8. Okay, so what we're going to do is we're going to do regression. So this is going to be list 1, list 2. Now, we don't want to put these numbers in our calculator because we're going to have, because the, right, that A would be the initial value. And if we're at 1900, almost 2000 to start with, that B value, like if you type it in with the 1900 to start, it's going to be like, it, you know, scientific notation, like to the negative 10. It's like crazy. So what we're going to do is we're going to call this. So this is going to be our L1 over here, and we're going to make this 0. So 1900, 0. So 1910 would be 10, and you're going to just keep working it up. So L1, 70, this would be 80, 90, and when you hit 2000, that's going to be 100. And this guy's going to be 103. So let's punch this on our calculator, and let's get a list. And so that's all the numbers punched in. I'm going to press Stat, Calc, Exponential Regression. I'm just going to push up. It's choice 0. Now it uses list 1, list 2 automatically, but you could do second L1, comma, second L2. And we hit enter. And we get something like 80 and change. And so there's my equation. So let's write that equation down. So I'm just going to slide it out of the way here. And what do I get? So it says y, a, b, x. You know what? Let's write this as a notation, function notation. So I'm going to call it p of t, population time, equals 80.86, bunch of sevens. So why don't we go to, two decimal, let's go to 3 decimal places. 868, okay, times 1.012, that makes that a 3. And that'd be a t up in the air. And so that was the question that your book asked. All right, so let's modify it. So here we go. Let's ask the question. So why don't we, make a graph for this thing? I don't even care about the graph, actually. When is P of T? So these are the extra questions. So extra. Okay. What was the population in 1955? And let's say, when did the population hit 140 million? And to the nearest year. And what was predicted population for 2013? So I am going to graph this thing, actually. So let's look at our calculator here. So our numbers went to 103 for the x. So I'm going to clear this out. And I'll type in our equation. And the more decimals, the better. So 80 point, what did we call it? 80.868 t, and we're going up to like 100, and I can see the number's going to be at like 290-ish. So why don't we go window, window 0. Now my x has to be at least 103, so we can say like 100 and, well, 100, 2013 would be 113, so let's say 120. So that'd be 2020. And the population has to go like 290.8. So I could look at the table and see what the number is. So 300, say 350. Let's hit graph. Let's see. I think that's pretty good. So take a look at the window again. Okay. So let's go back to graph, and let's do a couple here. So let's do the 1955 thing. So I could press trace and type in x is 55. That's 1955. So the population is 164.5. 164.5. And let's do 2013 while we're here. Let me just slide this out of the way. So 1955 is 164.5. And let's just make sure that makes sense. Yeah, that's right there in the middle, so that's good. And 2013, just press trace, and that'd be 113 for the x value. So 2013 should be ballparking 348.1, 348 million.1. So 3348.1, that's prediction. And when does it hit 140 million? Okay, so we go y equals, hit graph 140. Now, of course, you make a nice little graph that's going to show work for this. And we're going to second calc, intersect. 1, 2, 3. And 42.4. 42 and a half years. 42.5. So let's just, 42. When the publishing is 42.5. Oops. So what year was that? 1942. 42 and a half, it happened in the middle of the year. Okay. Now, here's a question. Is this a good representation? Now, we can ask another question here. So I Googled what the 2013 population was. So if population was really 316 million in 2013, what was the difference? So this could have been the question instead. Right. So I just staged it for you. Right. They could have just skip this one. Like skip this one and just go right to this one. So just subtract and you get your number. Let's try another one. All right, last type problem. So we've done, if you recall, logistic function. It was one of those ones that you had to memorize. And we did some problems on it too. And the logistic function looked like the letter S when you graph it. Something like this, right? And the horizontal asymptotes and like a big letter S like this, right? And this function was, so f of x equals 1 over 1 plus e to the negative x, right? And we said this happened a lot in like nature and stuff, especially, if you get this e thing floating around, think, like life sciences and stuff. So we can modify this, and I think we did actually. So this is logistic growth function. c over 1 plus a e to negative. That's not how it looks. E to negative kx. Okay. And this top number is our limit to growth. That's our horizontal asymptote. That's that top number. We did that in the past. So let's do a question for this. So there's so this was an example in your book, and it says that students spreading rumors, right? Students spreading rumors. Okay, and so it says, so it's S for student, T is the number of days, and they somehow come up with this formula, 1200 over 1 plus 39 e to the negative 0.9 t. All right, and they want to say, they're going to ask you some questions, and we're going to add to the example that was given in the book. All right, so here we go. First one. So once again, S is students, T is days. Okay, here we go. How many students know at the end of day 0? That's the initial, day 0. So at the end of day 0, what's S? What's S of T? Okay. All right, so what that means is, so we can graph this thing, and that might be a good way to do it. So let's just throw it in the calculator. Slide that over. And just be careful how you type it in, of course. So 1200 divided by parenthesis 1 plus. And that should be pretty good. And so that 1200 is like the top. So I'm going to do my window. So, and if you look at the values, we could look at the table just to get a ballpark. So 7 days is 1,100 people, 1186, 1197, 1199, right? And that 1200 is our horizontal asymptote. So like, when do you get really close to that 1200? So, right around day 10, day 11, right? So I can go to 12, let's say. So window 0 to 12. And that number is, so x0 and 1200. So maybe I'll do 1400 or something, or 1300. 1300 I'll do. And when I hit graph, I get that nice S shape, and it tops out. So how many people at the end of day 0? Well, go to table, go to 0, and we will see that there are 30 people. Well, there's another way to do it. I could have just put in a 0 here. So this would have been 1200 over 1 plus, well, if this is a 0, that means e to the 0 is 1. That's 1 plus 39. 1200 over 40 is 30. So that's another way to do it. What are the horizontal asymptotes? So why don't you write those down? There's 2. Y equals 0. Y equals 1200. How long for 1,000 students to hear the rumor? How long until 1,000 students hear the rumor. So I'm just going to graph 1,000 and calc intersect it. So 5.85 days, 5.86. So let's say end of, or 5.86, let's call it day 6. And so that's about it. All right, so now you have you have a little bit of time left. So what you're going to do is you're going to work on your review sheet for the quarterly, which is on Friday. Okay, guys, take care.